Good evening, everyone, and welcome back to AP Stats Notes Online. Going to continue our conversation on chi-squared tests. So when we last spoke, we were talking about chi-squared goodness of fit tests. Goodness of fit tests are great if you want to take one categorical variable and figure out if the distribution of that categorical variable is what is claimed to be or what you would expect it to be, and see if there's a significant difference in the actual distribution from a sample versus what you would expect to get if there's a claim out there, or if you think that each category in the variable is going to be evenly distributed or anything like that. But it's one categorical variable. So what happens if we want to, it's one categorical variable from one group. And so now we shift our focus into either looking at two different groups and how they break down over a categorical variable, or one group again, but measuring two categorical variables and see if there's an association between those two variables. The latter we will discuss next time around when we start talking about tests for homogeneity. When we start talking about tests for independence or an association. What we'll focus on today is what we call a chi-squared test of homogeneity. And what that means is for two different populations or two different groups, are the distributions across a categorical variable the same, or are they significantly different? Okay? So for example, 2014 Franklin Central AP Stat scores, how do they compare to the national results in the same year? Okay, so we have a 2A table here. One for the national scores, a row for the national scores, and a row for the Franklin Central scores. And 5 different columns, one for each of the possible AP exam scores. Okay, so you see those numbers there. You may need to change the numbers on your note sheet because your note sheet are using some other schools' scores. I thought it'd be more interesting if we used Franklin Central scores. So as I'm talking here, you might want to change those numbers over. Okay? All right. So, are they different? How do we compare them? Well, we talked about in Chapter 1 calculating a conditional distribution and taking a look at the distribution, those conditional distributions for each of the two different groups and comparing them and trying to find out if they're different or if they're roughly the same. We can do that now. So we can calculate the conditional distribution of the score for the national results and the FCHS results. Now, the hardest thing before about conditional distributions, and I still think it's kind of tough, is which way do we go, rows or columns? Well, since we're doing the distribution for the national results in FCHS, then obviously we're going to want to go across rows. Okay? So, I've done the hard work here for you, which is done that conditional distribution for you, and here's how they break down. You can see that 14% of the national scores were 5s, 21% were 4s, 25% were 3s, 18% were 2s, and 23% were 1s. Here at Franklin Central High School, 6% received 5s, 12% received 4s, 20% received 3s, 14% received 2s, and 49% received 1s. Okay? We do the conditional distributions in proportions because obviously there are different totals involved, and the proportions help it make comparisons a lot easier. Okay? Not looking good for the Franklin Central distribution here in terms of whether they are roughly the same as the national. I wonder if we can't do better this year, but we'll discuss that more in detail later. Okay? So there's the conditional distribution. It's great to see the numbers there, but it's a little bit easier to compare if you put these numbers into a bar graph. And so that is the next question on your notes. And that is, let me figure this out here, is here, make an appropriate graph for comparing the conditional distributions in Part A. Well, it's simple enough. We could do a side-by-side bar graph, and it wouldn't be that much more complicated, but these two bar graphs, since we're working with categorical variables, bar graphs are the most meaningful and easiest distribution or graph to make to show the distribution. So there you see it, the national versus FCHS. And so, do we think that FCHS's scores are different? First glance would say yes. The real question is, are they significantly different? And so we can take a look at that in a different way. Okay? But there's the graph. Again, not looking great for FCHS. I think that we can do better this year than last year's classes. But anyway, question C, is there evidence, and this is on the next page here, is there evidence that the FCHS AP Stat scores are significantly different than the national AP Stat scores? In other words, are the two populations different? Okay? Well, in order to determine significantly different, we have to do a significance test, or hypothesis test. And that's where this comes into play. Okay? So, our state plan do conclude. We're always sort of following that format, although we don't necessarily have to write that out. But anyway, how do we determine if there is a significant difference or not? Well, we're going to perform what's called a chi-square test for homogeneity. And we need to pick a significance level. 5% seems to be pretty standard and seems to work pretty well for us here. We need hypotheses. And so our null is always our statement of no difference. So what we're going to say is that the 2015 AP Stat scores for FCHS and the nation have the same distribution. In other words, they're homogeneous. Those two distributions are homogeneous. They're the same. That's our null hypothesis. What we're trying to find evidence for is that the 2015 AP Stat scores for FCHS and the nation do not have the same distribution. Again, it can be quite that simple as far as stating our hypotheses. Okay? So, plan. Let's plan this out. Well, we've already stated the name of our test, which we could put here if we really wanted to, but we're going to perform a chi-squared test for homogeneity at the 5% level. But it only makes sense to do this as long as some conditions are met, right? And our first condition is supposed to be our random condition. Well, we did not randomly choose students from FCHS or the national, from the national group. So how do we satisfy this random condition? Well, what we can say is that the individuals who have been counted are equivalent to a random sample of all years, okay? Or they're at the least representative of all national and FCHS future scores. That's the assumption we're going to have to make, and that's as close as we're going to get to satisfying this random condition. Okay? At least from the national score standpoint, when you take a year's grouping, you can, in terms of all years of the test given, consider 2015 to be, I said 2015, it's actually 2014. I'll get it right in a minute. 14 here, because we haven't taken the test yet. 14 here. Anyway, we can certainly at least loosely accept the fact that the national scores from 2014 are a random sample representation of all scores of all AP exams given in all possible years. I say it's a stretch only because obviously students are different from year to year. Groups are different from year to year. Now you get a big enough group and maybe the differences are small enough. But anyway, for the purposes of illustrating a chi-squared test, we're going to go ahead and go on with this. You might want to put a proceed with caution here and understand that we don't quite have random samples, but we're going to proceed anyway. Okay? The expected cell counts are all bigger than or equal to 5. Now, where does that come from? The expected cell counts. Where are expected numbers? If you remember before in our goodness of fit tests, our expected numbers came from assuming that the distribution of our one categorical variable was the same for all categories. And so we had to go through and use our proportions, our claimed proportions to figure out in our sample size how many we would expect in each category. The same is true here. What we want to do is we want to come up with how many, if the two distributions were the same, how many 5s, 4s, 3s, 2s, 1s would we expect from the national and the FCHS group? Let's go back to our table for a second and talk about how we might get that. Okay? Well, if we assume that the two distributions are the same, the national and the FCHS distributions are the same, okay, then what we want to do is sort of figure out, okay, first of all, how much of the total group is made up of the national group and how much of the total number of students taking the test are made up of FCHS students. And so we come over here to the total column and figure out, well, the national group, 165,263 is, and we divide that by 165,314, that is 0.9997% of the total there, the 165,314. Okay? And then the 51 would be the rest, right? So 51 divided by 165,314, that's very, very small, so obviously it's 0.0003% of the total group. So since the national group makes up 0.9997 of the total group, then we would expect of our total 23,140 people that got 5s to get to be in that national, the 0.9997 of those to be in the national group, right? Assuming that there's no difference between the two populations, the two groups, right? So then what we do is we take the 23,140 and times it by 0.9997 and realize that we would expect 23,133.06 to have gotten 5s in the national group. Okay? Then, of course, that means that we would expect 6.9, basically, to have gotten 5s out of the FCHS group, because 6.9 is 0.0003 of 23,140. And we do this across all the cells. Now think about what we're doing here. We found out how much of the total table number was in the national group. So we took 165 263 and divided it by 165,314, divided it by the total number. And then we took that proportion and we multiplied it by the total in the fives group, 23140. Okay, to find out our expected number in that particular cell. Well, all we've done here is we've taken the row total times the column total and divided it by the total in the entire table. And we can apply this to every cell in the table. We would take the row total, which is 165,263, and multiply it by the column total, 34546, and divided it by the table total, 165,314. And again, we're doing this because we're assuming that the two distributions are in fact the same. And if they are, then the number of 5s, 4s, 3s, 2s, and 1s should follow the same proportions as the percent of the table total that each of the two groups make up, if that makes any sense. Okay? So, in other words, to find our expected counts in our cells, we're going to take the row total times the column total and divide it by the table total. And that will give us all of our expected counts. Now, obviously, every cell in the national row is going to be much bigger than 5. All we really have to concern ourselves with are the FCHS cells, right? And so we'd want to take 51 times 34546 and divide it by 165,314. And we do that, we get 10.7. And then you'd want to take 51 times 40499 and then divide it by 165,314 and get 12.5. And then take 51 times 29589 and divide it by 165,314 and get 9.1. And then last but not least, take 51 times 37540 and divide it by 165,314 and we get 11.6. So all of those cells are bigger than 5. And so all of our expected counts are indeed bigger than 5. Okay? So that condition is definitely satisfied. And then our last condition, obviously each individual scores are going to be independent of each other. Again, we're not really randomly sampling from the population, although I guess we could do the 10% condition here because there are so many years that the tests have been given, and who knows in the future how long they will continue to give AP Stats exams. But if we're going to view 2014 scores as representative random samples from all future tests and all past tests, then certainly we are not sampling more than 10% of the population. So either way, the independent condition check has been satisfied. So we're ready to run our test. Okay? And again, as a reminder of where the expected cell counts are coming from, we just take the row total times the column total and divide it by the table total. Okay, and there's an easier way to do that, and I'll show you what that is in just a few minutes. Okay? So, we're going to use a chi-squared test for homogeneity. Now, just like our chi-squared test before, if you go to table C in your note packet, then obviously we need to know some degrees of freedom. Before in our goodness of fit test, our degrees of freedom were just one less than the number of categories. Well, the issue here is we're using a two-way table as opposed to a one-way table, and so our degrees of freedom aren't quite that easy to calculate. So we have to account for the rows and the columns, and the way we do that is we simply take 1 less the number of rows, 1 less the number of columns, and multiply them together. Here we have 2 rows and 5 columns, and so 2 minus 1 times 5 minus 1 gets us to 4, and so we're going to use 4 as our degrees of freedom. Okay? Remind me, and I will talk to you a little bit more about why this is called the degrees of freedom. We can do that when we're reviewing for the AP exam or when I get back. It'll only take a couple minutes for you to understand exactly why we call that a degrees of freedom. Okay? But anyway, that's how we're going to do it. Okay? What we need now is a p-value, a chi-squared statistic, and a conclusion. Okay? So, what we would do, well, we're going to run the test in our calculators. Okay? And I'll show you how that works in just a couple of minutes. But let's talk a little bit more about where our chi-squared statistic is going to come from. So again, our chi-squared statistic is always going to be our observed minus our expected squared divided by our expected, and we're going to sum that up for each cell now. Right? We're going to do this for each cell now. Okay? And so it's just like our goodness of fit test, only there's just more cells involved. So again, show a couple of terms. Show the first term, the last term, ellipsis in the middle, and then let the calculator do all of the other work for you. Now, how does that work? Well, you can kind of see here that we have to get into matrices in your calculator. So let's do that. Let's take a look at that real quick so that you can do your homework. Okay? All right. If we're going to run a chi-square goodness of fit test, then we're going to have to create a matrix. Okay? So, how do we do that? Well, if you go just above your x to the negative first power button is your matrix key. I'll try to zoom in here the best I can. So go second, x to the negative first, and there's your, it should give you a list of matrices, and we've got to go in and create one. So choose the first one and edit it. Okay? A matrix, if you haven't had any matrix, we've kind of taken them out of Algebra 2, so you may not know a lot about matrices, but the way they work is the dimensions of a matrix is always goes row by column. Rows by columns. And so our two-way table has 2 rows, but 5 columns. And so I want to type in a 5 over here. So I want to go 2 by 5. Okay? And then it puts you into that first cell, and now we're just going to type in our numbers from our two-way table. Okay? And you can arrow across as we do that. So 23137, 23137, you hit enter and it goes to the right. Your calculator will shoot you to the right for the next cell. And so 34540. Okay. Then we're going to go here, 40489. We're going to go here, 29582. We're going to go here, 37515. Okay, and then we got to have the rest of our rows 6.9, 10 point, I'm sorry, not 6.9, sorry, I was doing the expected count there, 3, 6, 10, 7, and then lastly 25. Okay, and so now your calculator should look something like this. Okay, now that we've created our matrix, we can quit out of this, second quit, and go grab our chi-squared test. Stat, tests, chi-squared, and we just want to do a chi-squared test, not a goodness of fit test. Okay? And here's all it needs. The calculator just wants to know where the observed counts are, which right now is in matrix A, and it wants to know which matrix to put your expected counts in. Now, notice that. That's what I meant before by we don't necessarily have to go in and do row total times column total divided by table total for every cell. We can let the calculator run the test and then go look at matrix B, and that will be your expected counts. So let's do that. We're going to stick it in matrix B. We're going to hit calculate, and you'd think it would take longer than that, but bam, there it is. There's your chi-square statistic. There's your p-value, and your degrees of freedom of 4. Okay? Let's go write that down real fast. Okay? I'm not going to take the time to write the expected counts in the parentheses here. You can do that if you'd like. We're just going to go take a look at them in just a second. So our chi-square statistic, once we show our work with the terms here, 23137 minus whatever that expected count is squared over whatever that expected count is plus ... plus we go 25 minus whatever that expected count was squared all over whatever that expected count was, and that gets us to our chi-square statistic of 20.98. Then we say our p-value, which is pretty small, 0.000319, so 0.0003 works. Okay, and we've already set our degrees of freedom of 4, and now we're ready to conclude. Okay, and so we can do this real quick. Well, since our p-value is certainly less than our alpha, okay, then what we can say is we reject H naught. Okay, and so we say we have convincing evidence, or we have significant evidence that the FCHS scores are different than the national scores. Okay? Which from the distributions we kind of could tell. All right? So anyway, the conclusion is kind of the same as we've done all along. Now, our expected numbers, I wanted to show you that. Now that we've run our test, if we go back into second matrix, which is above your x to the negative 1, now you see that matrix B has changed into a 2 by 5. And we can go take a look at it by arrowing over to Edit and then down to Matrix B. And there are all of your expected counts. Now we should be able to compare those expected counts to what we put up here, at least for the first couple. Of course not because I erased them, but we can at least see that the calculator does a little bit different, it doesn't do it, shows a different number for the expected counts for each of the FCHS cells. And that's due to rounding. Okay, there's a bit of rounding involved there. So 6.9 versus 7.1 is pretty close. 7.1 is what the calculator should be showing right now. But so you arrow across, and they're all pretty close to what they needed to be. So anyway, you can go, if you want to be sure that the large sample size condition has been satisfied, you can go check your expected counts by simply doing the test and then go and look at the matrix. Okay? But anyway, that's your chi-square test for homogeneity. And a lot of the same things that we've done before, but it gets a little bit more complicated when we've got a two-way table. Okay? Now, let's do this for something other than something like these scores where some of the conditions were kind of shaky anyway. Okay. In 2002, an article in the Journal of the American Medical Association reports the results of a study designed to see if the herb St. John's wort is effective in treating moderately severe cases of depression. The study involved 338 subjects who were being treated for major depression. The subjects were randomly assigned to receive one of three treatments, either the St. John's wort Zoloft or just a placebo. Okay. For an 8-week period, the table below summarizes the results of the experiment. Either they experienced a full response. Okay. Anyway, sorry about that. So they either experienced a full response, partial response, or no response, and so there's your table. Are the differences among the groups statistically significant? Now, normally you will not get the expected counts in your table if this were to pop up on an AP exam or even a test in here. You would not get the expected counts in the table as well, but there they are. So are the differences among the groups statistically significant? Well, to find out, what do you want to do? How about we run a significance test, right? We don't have to worry about doing the conditional distribution and then the bar graphs. We can just go straight into running our test. So we need to state our hypotheses, our null. Again, our null is our statement of no difference. And so that means we are going to assume that the three treatments are equally effective. There's no difference in any of those treatments in treating moderately severe cases of depression. Okay? And so we are looking for evidence of a difference. So the three treatments are equally effective in treating moderately severe cases of depression is our null. Our alternative is there is a difference in the effectiveness of the three treatments in treating moderately severe cases of depression. Okay, you can word those however you want. There may be a way to word those two hypotheses so that we can get that simply inserting the word not into one of those two to make them different. Okay? Alright, so let's plan this sucker out. Okay? Random. Was our random condition met? Well, it says the treatments were randomly assigned, so yes. Large sample size. The expected counts, which were in the parentheses, are all greater than 5. Again, we can see that once we run our test and have the calculator dump the expected counts into a matrix. Okay? Do notice that we're talking about an experiment here. And so the random has to talk about the random assignment to the treatments, not a random sample. Okay? And then obviously our independent language changes a little bit as well. Knowing the response of one patient should not provide any additional information about the response of any other patient. Okay? And so that is what we're talking about with the independence check, not a 10% condition. Okay? Because we're not sampling. All right. Our chi-squared statistic, and this is what I was talking about before, where you want to just show a couple of terms. I would prefer you do a first term, last term kind of a thing, but you just got to show someone that you know where the statistic is coming from. And so this is in that first cell, 27 minus the 30.4, square that difference, divided by 30.4, and same thing for the next term. Okay. Let's take a look at the calculated version one more time here, okay? Make sure that we're good with this, okay? So I've got to create a matrix for the observed counts. So hit second x to the negative first. I'm going to arrow over to edit and then arrow down to C and create a C matrix here. I'll show you how to change that if you ever need to, okay? So our matrix needs to be row by column, 3 by 3. So we go 3 by 3, and it creates that for you. Now we got to type in the observed counts. So 27, and then 27, and then 37, and then 16, and then 26, and then 13, and then we go 70, 56, and 66. Now we're done, so we go into our chi-squared test. where we go stat tests, arrow to chi-squared test. Now, my observed are no longer in matrix A, they're in matrix C, so I gotta go choose that one. Okay, so I just simply go to second, x to the negative first, and choose C. And I want the expected to be not put in B, but put in D. So arrow down to D and hit enter. And then I calculate, and there's everything for us. So our chi-squared statistic is 8.7, which we're going to want to write down. Our p-value is 0.069, and our degrees of freedom, again, are 4 because we do one less number of rows, one less number of columns, and that's going to be 2 times 2, okay, which I'm pretty sure is 4. Okay, so we write down our chi-squared statistic, it's 8.72. We write down our degrees of freedom of 4, our p-value of 0.0685, which you don't have to do chi-squared CDF. Certainly can if you want to. Now that you have the chi-squared statistic, we can review that at another time. But we already have our p-value from our calculator, right? And so our conclusion, 0.0685 is definitely bigger than 0.05. So we're going to fail to reject here, okay? I'm not sure that we ever actually went through and defined our test, which we should have defined our test and defined our alpha. That's shame on me. Okay, but our conclusion, since the p-value is greater than alpha, we fail to reject the null. We do not have convincing evidence that there is a difference in the effectiveness of the 3 treatments in treating moderately severe cases of depression. Okay. And last but not least, it asks us to interpret the p-value in context. The p-value is 0.0685. Remember that the general way to interpret a p-value is it is assuming that the null is true. This is the probability that a sample would give you a result as big or bigger than this one did. Something to that effect. Now we need some context. So we could say something like, assuming that the treatments are equally effective, that's our null, assuming the null is true, assuming the treatments are equally effective, the probability of observing a difference in the distribution of responses among the 3 treatment groups as large or larger than the one in the study is about 0.07, about 7%. Okay? Is how we can word the p-value there. Now, if we do reject the null, like we did back here in our AP exam score distributions, so we reject the null. So now we have enough evidence to suggest that the FCHS scores are distributed differently than the national. A very logical follow-up question would be, okay, which score was FCHS's distribution the most different from the national scores, right? And so we would want to do a follow-up analysis. And in order to do that, we would have to see the chi-squared components. Remember that from the goodness of fit test? Well, unfortunately, the calculator doesn't give that to us. If you're ever asked to do a follow-up analysis on the AP exam or on a test in here, that you would be given a mini-tab output, and I can show you that when I get back, and kind of show you how to look at that and try to figure out which one contributed the most to your chi-squared statistic. Okay? Anyway, that's your test for homogeneity. We'll stop here and pick up more in the next set of notes.